Ever pondered about how to find the inverse of a matrix and why it's crucial? Well, let's dive right into it. A matrix is a set of numbers arranged in rows and columns like a grid. It's a handy way to represent and manipulate multiple equations at once. Now, an inverse of a matrix is much like a reciprocal of a number. Just as multiplying a number by its reciprocal gives us 1, multiplying a matrix by its inverse gives us the identity matrix. But why is this important, you might ask? Inverse matrices are key to solving systems of linear equations. Think of it like cracking a code or solving a puzzle. The inverse matrix holds the key to unlock the solution. From computer graphics and cryptography to economics and engineering, they're everywhere. Knowing how to find the inverse of a matrix is a vital skill in various mathematical and scientific fields. So, let's take this journey together and unravel the mystery of matrix inversion. Before diving into the process of finding the inverse, it's essential to grasp the concept of the determinant of a matrix. The determinant is a special number that can only be calculated for square matrices. This number is incredibly significant as it gives us insights into the properties of the matrix. For instance, if the determinant is 0, the matrix does not have an inverse, and we say that it's singular. If the determinant is not 0, then the matrix is invertible. This is why understanding the determinant is a crucial step towards grasping matrix inversion. Let's illustrate with a simple 2x2 matrix. The determinant is calculated as the product of the elements on the main diagonal minus the product of the off-diagonal elements. So for a matrix with elements A, B, C, and D, the determinant would be A times D minus B times C. Remember, the determinant plays a key role in determining whether a matrix has an inverse or not. Not all matrices have inverses. So, what's the condition for a matrix to have an inverse? Well, let's delve into this. For a matrix to have an inverse, 2 conditions must be met. First, the matrix must be a square matrix. That means it should have the same number of rows as columns. Now, even if you have a square matrix, it doesn't mean it will always have an inverse. There's another condition to keep in mind. This brings us to the concept of a determinant. The determinant of a matrix should not be 0. If the determinant is 0, the matrix is considered singular, and it doesn't have an inverse. But if the determinant is not 0, then the matrix is called non-singular or invertible. And yes, you guessed it right, these matrices have inverses. So if you have a square matrix with a non-zero determinant, you can find its inverse. Now that we understand the prerequisites, we can dive into the steps to find the inverse of a matrix. Let's start with a simple 2x2 matrix. To find its inverse, we'll follow 4 main steps. Step 1, find the matrix of minors. The minor of an element in a matrix is the determinant of the smaller matrix formed when its row and column are removed. For a 2x2 matrix, the minor of an element is simply the remaining element. Step 2 is to form the cofactor matrix. The cofactor of an element is its minor, multiplied by -1 to the power of the sum of its row and column numbers. This might sound tricky, but remember, in a 2x2 matrix, this means we just swap the sign of the top right and bottom left elements. Step 3, transpose the cofactor matrix to get the adjugate. Transposing simply means swapping rows with columns. In a 2x2 matrix, this means swapping the top right and bottom left elements. Finally, step 4, divide each element of the adjugate by the determinant of the original matrix. This gives us the inverse. That's the basic process, but let's walk through an example to make things crystal clear. Imagine a 2x2 matrix with elements 1, 2, 3, and 4. For step 1, our matrix of minors is simply 4, 3, 2, 1. Step 2, the cofactor matrix swaps the sign of the top right and bottom left elements, giving us 4, -3, -2, and 1. Step 3, the adjugate swaps the top right and bottom left elements, giving us 4, -2, -3, and 1. For step 4, we divide each element by the determinant. In this case, the determinant is 1 times 4 minus 2 times 3, which equals -2. Therefore, the inverse of our matrix is -2, 1, 1.5, and -0.5. And there you have it, the inverse of your matrix. But remember, Practice makes perfect. You might be thinking, why go through all this trouble to find an inverse? Well, the importance of matrix inversion extends far beyond the classroom, making significant contributions in a variety of fields. For instance, in computer graphics, matrix inversion plays a crucial role. When creating three-dimensional models or developing animations, computer software uses matrices to transform geometric data. The inverse of these matrices is used to manipulate these models, allowing for scaling, rotation, and translation of the objects. Without matrix inversion, the vibrant, lifelike graphics we enjoy in video games and movies would be significantly harder to achieve. Cryptography, the science of encoding and decoding information, also relies heavily on matrix inversion. In certain encryption algorithms, matrices and their inverses are used to scramble and unscramble data, ensuring that our sensitive information remains secure. The strength of these encryption techniques often lies in the complexity of the matrix inversion, making it difficult for unwanted parties to decode the information. In the realm of physics, matrix inversion is indispensable too. It helps in solving systems of linear equations that frequently arise in various branches of physics. For instance, in quantum mechanics, matrices and their inverses are used to calculate probabilities and predict outcomes of experiments. Moreover, matrix inversion is a fundamental operation in linear algebra, a branch of mathematics that deals with vectors, vector spaces, and linear transformations. It's used to solve systems of linear equations, a common problem in mathematics and engineering. In these systems, the coefficients can be placed in a matrix, and the inverse of this matrix is used to find the solution. So you see, matrix inversion is not just an abstract mathematical concept. It's a practical tool